Okay, so real quick review of Chapter 4. We're going to talk about atomic structure again and isotopes, all right? Now, the current model that we use of the atom is called the Electron Cloud. And an atom is the smallest particle of an element that retains the physical properties of that element, all right? And atoms are composed of three subatomic particles, protons, neutrons, and electrons, okay? Protons, neutrons, and electrons. So if we make ourselves a little chart, we can draw a really old-fashioned picture of an atom, one like you have seen in the 8th grade, okay? Okay? What's the chocolatey center of the atom called? Sam, what do you think it is? The chocolatey center of the atom? Called the nucleus. That's exactly right. So the nucleus is in the middle, and we have two particles in here, right? You know, what two particles are they? Drew, you tell me. We got protons and neutrons in here. And then out here, outside of the nucleus, we have this cloud. And this cloud is built of what particles? Electrons. And I like to just put a dash for an electron, okay? Well, I'll just write an E for y'all right now. So we have protons, neutrons, they're in the nucleus. And then electrons are out here in a cloud. And we'll see that model later. Okay. Very simply, protons and neutrons are the only thing that have mass, okay? And what is wrong with this picture of the atom? Does anyone know what's wrong with this picture of the atom? There's a lot of things. What's wrong with the nucleus? Let me be more specific. What's wrong with the nucleus of this atom? Does anybody have an idea? Do you remember? That's okay. The problem is, if this was a picture of the atom, the nucleus to scale would be about like that right there, or smaller. The nucleus is very small, okay? Very, very, very small. And all of the mass is in the nucleus, okay? Now, that I said that term, all of the mass is in the nucleus. We're going to talk about the two things that are in the nucleus. The two things that are in the two particles are protons and neutrons, all right? All right, and these are the ones that are in the nucleus. So if we're thinking about this, we have mass and charge. All right. So we're talking about protons. What is the mass of a proton? That's right, everybody. The mass of a proton is 1, and then the charge of a proton is positive. That's right, positive 1. And then neutrons, the mass of a neutron is 1. It's just like a proton, has the same weight. Protons and neutrons are identical in weight, but a neutron is neutral, has a charge of 0. Okay? So all of the mass is in the nucleus, because the third particle is an electron. It's outside of the nucleus in a cloud. It has no mass and a charge of -1. Now, looking at this chart right here, what two of these particles are attracted to each other? That's right, protons and electrons. These guys are attracted to each other because of their opposite charges. And the really famous saying is, opposites do what? Attract. That's right. So if we go back here and we look at a picture, let me mute this so we don't have this crazy sound. If we go back here and we look at a picture, our most modern picture of the atom, you'll see the electron cloud, okay? So the nucleus would really be smaller than this. And the positive charge is in here. All the protons are in here. And the electrons appear out here. And the reason they don't appear further away or somewhere else is because they're attracted to the charge in the nucleus. So the negative and positives attract each other, and that's what keeps atoms compact. Does that make sense? Is the charge of the atom. Okay. So that's our basic structure of the atom. Now, when we take a look at a card, let's draw a card for an atom real quick. And I always call these cards because I like to think of the periodic table as a deck of cards laid out. And literally the inventor of the periodic table, there were several inventors, but the one that has the most credit, he literally had information written on cards about all the elements, and he laid them out on a table and sort of played a game of solitaire with them, and that's how he came up with the periodic table. Let's take a look at this guy. Let me think of someone I haven't done yet as an example. We'll do boron. Boron is its mass is 11, and its atomic number is number 5. Okay, so this is a card for boron. Boron's most popularly occurring atom has a mass of 11. Some of them have a mass of 10. Some of them have a mass of 12. But most commonly, boron would have a mass of 11. Okay? Boom. That number 5 is called the atomic number. And it stands for the number of what, Sam? Protons. Now, if this atom is neutral, okay, if we're talking about an atom that's not in a relationship with other atoms, then the number of protons and the number of electrons will be the same. All right? So you'll hear people say, well, that stands for the number of electrons. No, it doesn't. This stands for the number of protons. But if the atom is neutral, then it's the same thing. Right? Does that make sense? Because it would have the same number of protons and electrons. All right? Let's go down here. This is the number of protons up here. It's called the atomic number. And this is the atomic mass. All right? The atomic mass is what two particles have? Yep. Protons and neutrons. So we can look at this. We know the number of protons. We know the atomic mass. So to find the number of neutrons, that's not actually written on the card anywhere. To find the number of neutrons, we have to do a math problem. And we have to say the atomic mass minus the number of protons equals the number of neutrons. All right? So the number of neutrons in boron 11 is going to be 6. All right, we're just subtracting these two numbers. Now this is nothing new. Okay? This is all stuff that you would have had on an 8th grade science test, all right? Now the next thing you need to know is not every atom of boron is boron 11. Here is a card. I'm going to redo it. Here is boron 11. And here is another atom of boron called boron 10. These two atoms are different versions of the same atom, and they only differ by their weight. So these two are known as what? What's the word? Anybody want to yell it out? These are both what? Isotopes. That's exactly right. Isotopes. Now, a lot of students think, well, this is the regular atom, and this is the isotope. No, isotope just means versions of the atom, so they're both isotopes. Okay? All right, isotopes. They're both isotopes. And they differ in atomic mass. And since the atomic number is obviously going to be the same because it's boron, then they have a different number of what? Of what particles? Neutrons. That's exactly right. They have a different number of neutrons. Okay? And if we were going to write these cards down as words, we would call this one, we would write boron-11, or we would call it boron-10. Or if we're going to start writing a mathematical equation, if we're going to write a mathematical equation representing nuclear decay, like alpha, beta, or gamma decay, we would say 11 over 5b, and then we would start out for boron 10, we'd say 10 over 5b. Does that make sense to everyone? So the last thing we could do to wrap this all up is take a look at a chart like this. Take a look at a chart like this. Okay? And I know we looked at this yesterday. So, nucleons is a word for protons and neutrons because they're in the nucleus, okay? The nuclear charge is the number of protons. So the nuclear charge, right? Let's do atom C here, right? It says the mass number is 56 and the symbol is Mn. If we know the symbol is Mn, we can look on the periodic table and we can find Mn, and we know that the number of protons will be 25. Okay? 25. So there's 25 positive charges in the nucleus. So the nuclear charge is plus 25. All right? If there's 25 protons, then the atomic number is what? 25, because 25 is the number of protons. The same thing. The atomic number is the number of protons. All right? It has a mass of 56. It has 25 protons. So it must have how many neutrons? We got to go from 25 to a weight of 56. 31. All right? 31. And then if this atom is neutral, if it doesn't have a positive or negative charge, if it has 25 protons, it must have how many electrons? 25. And then nucleons is the total number of particles in the nucleus. So that would also be equal to the atomic mass because the electrons basically weigh nothing. So that's how we can work our way through any of these. Does that make sense? That's how we can work our way through any of these problems. And that's it. That's the total review. That's how far we got yesterday. Does everybody agree with that? All right.